All right, this is 4025 MAA mechanics tutorial number 7. And this is about second moment of area and bending stress. So let's start by giving a quick recap on the second moment of area. Remember, the second moment of area about an axis is a number that tells you the distribution, how much an area is distributed around a certain axis. So for rectangles, where you might have the x-axis in this direction and the y-axis in this direction, you have that Ix is bh cubed divided by 12, where this is b and this is h, and Iy is, of course, hb cubed divided by 12. For circles, circle, just as a reference, of course, as you might imagine, for a circle, you have exactly the same second moment of area around any axis. It's axisymmetric. And so you have that Ix is the same as Iy, which is pi diameter to the power of 4 divided by 64, where the diameter is this one. Now let's solve tutorial exercise level 1. So we want to determine the second moment of area about the x-axis. Now look, the x-axis is here, so it's not the centroidal axis that we were expecting. We need to use this axis x. So we will take advantage of the parallel axis theorem, which I'm going to recap here. Parallel axis theorem says that the second moment of area about any axis parallel to the one axis that you know is equal to the second moment of area of that you know about the parallel axis plus the area of the shape times the distance between the two axes squared. So let's apply the parallel axis theorem to this shape. So let me draw this first. Okay. So we know that this is, let me say that this distance here is 150. Let's call this h. This distance here is b. And the radius, let's call this r, small r. Yeah, that's it. So we know b is 100 millimeters, h is 150 millimeters, and the radius is 25 millimeters. We want to find the second moment of area with respect to this axis x. Do this in orange. This is our axis of interest. But we know that rectangle and circle have their centroidal second moment of area that we already know. So let's find, first of all, the centroidal second moment of area, let me put this here. The centroidal second moment of area. Let's call this XC, this centroidal C axis, because this is the X axis that we want. So I know that the second moment of area of this shape with respect to this axis is just the large rectangle minus the small circle. I can do this. I can always do this. I can take the second moment of area of this complex shape is just the second moment of area of this large rectangle minus, because I'm cutting a hole out of it, so minus the second moment of area of this circle here. So let me do that in formulae. Formulae, I'm saying that Ix, which is the one I want, Ix, this one, is Ix of the rectangle minus Ix of the circle. Of course, of the rectangle and circle, I don't know Ix, I know Ixc, so let me use the parallel axis theorem here, exactly like this. So this one becomes Ix is Ixc of the rectangle plus the area of the rectangle times the distance between the two axes squared. Now, distance is this distance here. Let me do this. This is the distance I'm looking for. Which, of course, is h divided by 2. Now, this is Ixr, so minus, and this is Ixc. Ixc, so Ix of the circle is just Ixc of the circle. You know, it's a bit complicated to call it all X. Let me change this name to A. Let's use Y. So it's more convenient. Though it's not used in a conventional way, you might agree with me that this is exactly what we are doing. It's the same thing. So Iy of the circle, so I of the circle with respect to this y-axis, plus the area of the circle times the same distance squared. Now this squared is the same for both. This d and this d are the same because both the rectangle and the circle have the centroid at the same point. So the centroid is here for all of them. Okay, so we can just explicitate. Let me take this. There we go. So we know we are explicitating this one. So if I do this, Iy of r, so what is the I of this rectangle with respect to this y-axis is, of course, bh cubed divided by 12. Plus the area of the rectangle, which is b times h, times the distance squared. Do you agree with me? This is h squared divided by 4. Because this distance d is h divided by 2. So squared is h squared divided by 4. Minus Iyc. So again, I told you that for the circle it's always this. So pi d to the power of 4 divided by 64. So it's pi twice the radius to the power of 4 divided by 64 plus pi r squared, the area of the circle, times the same distance squared, which is still h squared divided by 4. And these are all numbers. B, H, and R are numbers. So B, H, and R are all numbers. And that's it. So we can just do the calculations. Now, according to the calculations, of course, this will be 101 times 10 to the power of 6 millimeters to the power of 4. And as you can see, this makes sense because this is meter cubed, this is millimeter cubed times millimeters. So this is millimeters to the power of 4. This is millimeter squared times millimeter squared. This is also millimeters to the power of 4. And everything here is also millimeters to the power of 4. So this makes sense. Okay, any questions on this? Is this clear? It's quite easy. Not very complicated at all. So we are making use of the parallel axis theorem to use to simplify, say, the calculations, to make the calculations a bit easier. Now let's solve exercise level 2. We have a member having dimensions shown is used to resist an internal bending moment of 90 kilonewton meters. Determine the maximum stress in the member if the moment is applied about the z-axis or about the y-axis. So about the z-axis, we are looking at this moment here. About the y-axis is this moment here. You agree with me? Around the y-axis. So instead of bending up and down, like in this case, this is bending up. So for a moment around the y-axis, this will be bending right. So we have to redo the calculation twice, once for this moment, which is shown here, and once for a moment that we have to apply about y. So let's recall bending stress. So for bending stress here, okay, on a rectangular section, you have that the stress is always 0 at the centroid. So this is the centroid. So at the centroidal line, we have no stress. And then it increases or decreases based on the distance from the neutral axis. So it's a linear function. So it's the equation of a straight line. And the stress gets larger and larger as you move away from the neutral axis. This one is the neutral axis. So the more you move away from the neutral axis, the larger is the stress. So that means that the most stress points of this section are this one and these ones. So the top and bottommost fibers. So let's also recall the sigma is m divided by I times y. And let's say that y is this coordinate here. So as you can see, as I move y, as I move away from y, this is my origin. So if y is positive, this becomes positive. And if y is negative, this becomes negative. So this is a compressive stress at the bottom, the tensile stress at the top. And we also need the second moment of area, very important. M is the internal load. All right. Let's say that this is a linear distribution, linear. Okay, so what we have here is this section. So let me draw this in this direction. So of course the centroid is here. Let me say that this is B and this is H, where B is 200 millimeters and H is 150 millimeters. Now, the moment is applied such as the top part, see, the arrows must go outside the bottom and inside the top. This is the stress distribution we were looking at. Out from the bottom into the top. So the top part is in compression and the bottom part is in tension, whereas there is no stress in the middle because that's where the centroid is. This is the stress. Mm-hmm. So this is the distribution. This is the distribution. Oh. Yeah. Positive sigma here, negative sigma here. So if I look at this in this direction, I must have a positive sigma at the bottom and a negative sigma on the top. Use this. As you can see, since it's completely symmetric, we have the same value at the top and the bottom. How do I know we have the same value? Because these two are similar triangles, okay? Because this angle is the same for both. If this distance is the same as this, that means that this arrow is the same as this. So we have negative sigma at the top, positive sigma at the bottom. But how much is this sigma? Well, how much is very easy. We use the sigma equals m over I times y. Now m is, well, let's say m over what is the second moment of area with respect to this z-axis. I'm drawing it as I see it here. So sigma is along the x-axis. So sigma x is the m around z times yz, sorry, divided by yz times the y coordinate. And if I explicitate this, I get that sigma x is mz divided by bh cubed divided by 12 times the largest stress, so sigma x max is this one. So let's call this minus sigma max and plus sigma max. So the largest stress is where y, this is the y-axis, where y is the largest, so either here or here. And how much is this? This is h divided by 2. So this gives 120 megapascals. If I'm using millimeters, this gives 120 megapascals. Okay, so let's do the calculation properly. So what I have is that sigma x max equals mz is 90 kilonewton meters. So let's use Newton millimeters. So kilonewton meters in Newton millimeters is, so from kilonewton meters to Newton millimeters, I have to transform this one into newtons first. So this is 1000. And this meters into millimeters. So it's 1000 again. So I have to multiply everything times 10 to the power of 6. So it's 90 times 10 to the power of 6. And this is Newton millimeter squared. So this is, Newton millimeters. Divided by everything in millimeters I want here. These are millimeters to the power of 4. So it's 200 times 150 squared. It's 200 times 150 cubed divided by 12. And this is millimeters. And this is millimeters cubed times h divided by 2, 150 divided by 2. And this is also millimeters. So overall, I have Newton millimeter squared at the numerator and millimeters to the power of 4 at the denominator. So in the end, I get 120. So if I do this calculation, I get 120 newtons per millimeter square, and this is just megapascal. Let me call it megapascal. And this is what I wanted to know in the end. Okay, don't need this anymore. All clear? Looks like so. Okay, so let's do the other one. So the other direction. What happens if I change direction? So applying the moment around the y-axis, how does my formula change? Well, sigma is still around x. See, if I change this, let's say I'm doing this around the y-axis, then in this case, now this part is going out, and this part is going in. So it changes like this. Okay, so this is the new distribution. And so I can just change everything around, I can just swap everything. So sigma x max, look, sigma is still in direction x. So the stress doesn't change direction. The direction of the stress is always the same. Now we just have this side in tension and this side in compression, as opposed as this side in tension and this side in compression that we had earlier. So we are changing this to have m of y over iy. And of course, now what's important is not the y coordinate, it's the z coordinate. See, this blue distribution grows according to the z-axis. It doesn't grow according with y. It's constant along y, so we are using z. Now, how do you know? It's always easy. You look at this is the direction of the stress. This is always the direction of the moment. And so whatever is left, sigma x, y, z. Look at this one here, x and z, so I have to use y. You must always have a complete set of coordinates. All right, so let's do this calculation, and this becomes my, which is the same. Now, of course, iy is not hb cubed, as it's not bh cubed divided by 12 anymore, it's hb cubed divided by 12, because we are swapping the axes. And z max is, the largest z is b divided by 2 now. So if I redo this calculation, I get that my is still 90 times 10 to the power of 6. Just applied in a different direction. It's the same moment. iy is 150 times 200 cubed divided by 12. Times 200 divided by 2. And this is 90 megapascal, I believe. Yes, 90 megapascal. We are still using the same units. So this is Newton millimeters. This is millimeters cubed, millimeters to the power of 4. This is millimeters. So we get megapascal in the end. And so if I redraw this and I have a look at the distribution, now the distribution that I'm looking at is this one. Let me take this one down a notch. So my new distribution, this one is this. So with the moment around y, I have arrows going out of here and in here. So this is positive sigma here, max, and negative sigma max here. This. Okay. So let's have a look at the section again, because I want to see where is the largest stress in total. And it's not required by the question, but it's still good if we can see what's going on in this section in particular. So when the moment is around Z, then this splits the area in two, where the top part is in compression, negative, negative, negative. And the bottom part is in tension. Conversely, if I apply the moment around this axis, then I have this area split into two, but in this other direction now. And I have negative all here, so compression on the right. And tension on the left. So as you can see, the largest, these ones compensate each other. So if I apply the moments at the same time, these ones, these stresses, one is positive, one is negative, so they alleviate each other, they compensate each other here and here. And the largest stress resides at this corner, at one of these corners here, depending on how strong are these moments. Yeah, because here you have the largest positive stress, largest tensile stress, and here you have the largest compressive stress. Again, this is stuff, this is advanced stuff that you'll probably do much more in detail next year, so don't worry too much about it. Let's see if I can make this. There we go. All right, so let's solve the last question. It's very easy. Well, this is a bit more complicated, of course. Now I require your input. We want to calculate the stress distribution. This is a moment that is given, M, 8 kilonewton meters. And again, same thing, we want to find the maximum bending stress. It's not given the direction, so let's say that this is the x-axis. And this is the y-axis. And this is the z-axis. So how do we find the largest bending stress? So this moment is, of course, as you can see, the moment is around the z-axis. So that means that sigma x max is the moment around z divided by iz times the y coordinate, x, y, z. So we accounted for everything. So the largest y coordinate, of course, is 100 millimeter, no, 110, I believe. So this goes here. I think I screwed up because this should go here. This go here, and this should go here. Yes. Okay. So this distance here, the largest distance, y max, is 120, no, 110 millimeters. Okay. So we know that y max is also given. So what's left? Mz is given here, 8 kilonewton meters. So we must find Iz. So let's find Iz. So let me redraw this. Looks to me like this. It's probably, no, it's longer than it is thick. Yeah, this should go. Okay. Let me check if this is in the center. Yeah, looks like it. So the centroid, of course, is here because this section is completely symmetric. And now I have a question for you. How do you split this? So how many rectangles we need here? So how many simple shapes? While I draw the axis, and I told you that this is the z-axis. And this is the y-axis. So you can do this in many ways. You can say this is rectangle 1, rectangle 1, rectangle 2, rectangle 3, rectangle 4, and square 5. But it might be too complicated because you have too many rectangles. So one way I would do it is, let's say, sorry again, this is rectangle 1, and then I can add rectangle 2, but I have an issue, and the issue is that I am counting this square here this square, I'm counting it twice. So what I will do is rectangle 1 plus rectangle 2 minus the square. So let me call this rectangle 1 plus rectangle 2 minus the square. Okay. Okay, so let me just go on about it. Let me just also use the dimensions I want. Let's say that this dimension here is capital H. This dimension here is capital B. And then I say the thickness is the same. So let me call this dimension here the thickness T. And that should be it. Yeah. So let me do this. I of Z, that's what I want. I of Z is IZ of rectangle 1 plus IZ of rectangle 2 minus IZ of the square 3. And all of these, as you can see, all of these refer to the same axis because they are all aligned. All these ones have the same centroid, this point, and the center of the rectangle. This point, and this point are the same point. And that's very convenient. So we don't have to use the parallel axis theorem if you choose this. If we had chosen this rectangle, this rectangle, this rectangle, and this rectangle, and this square, well, this rectangle has this centroid, this has this, this has this, this has this. We have 5 different centroids. Now these 3 are aligned along IZ. So for this one, you can take them without the parallel axis theorem, but these 2, these are not on the z-axis, so you need to use the parallel axis theorem with this distance and this distance. Okay, so again, different way of doing it. Some of them are more complicated than others. So try to be smart about it. So IZ of 1 is just rectangle 1. So rectangle 1 is just B. In this case, B is T. This one is T, and this one is capital H. This one is B, and this one is T, and this one is T, and this one is T. So this one, this is equal to IZ for the entire section equals BH cubed, so T capital H cubed divided by 12 plus BH cubed divided by 12 minus, of course, B and H here are the same. So a square is just a rectangle with the same, with equal edges. So it's T to the power of 4 divided by 12. That's it. So if you do this, you get a number. And which number is that? Let me open MATLAB. So I want to be very, well, let's not open MATLAB, it's too complicated. And I said that T is 20. Oh, let me put them here. So T is 20 millimeters. Capital H is 220. Capital B is 120. So I'll go on Wolfram alpha and I say that this is 20 times H cubed, which is 220 cubed, divided by 12, plus B 120 times 20 cubed divided by 12 minus 20 to the power of 4 divided by 12. This is a number. It's 17.81 times 10 to the power of 6. This is 10 to the power of 7. So yeah, so 17 times 10 to the power of 6. This is equal to 17.81 times 10 to the power of 6 millimeters to the power of 4. See, I don't like 10 to the power of 7. I like these to be multiple of 3 because we are engineers. So I'm just copying the result. And this is the IZ that I want. And finally, Y max is given. IZ I found, MZ I found. So I can just say the sigma max is just MZ, so I said it's 8 kilonewton meters, so it's 8 times 10 to the power of 6 Newton millimeters, divided by 17.81 times 10 to the power of 6, these go away very nicely, millimeters to the power of 4 times 110. And this is equal to, use the calculator, 8 times 110 divided by 17.80, 49.4 megapascal. Okay. Now, of course, I have some space here, so let me redraw this one. So let me copy this because I want to show you the stress distribution as well. The stress distribution looks like this. This is the top, this is the bottom, this is the centroid. And so all of these dotted lines. And this is the stress distribution. Passing through the centroid, there we go. This is sigma max. This is sigma max. This one is positive and this one is negative. How do I know one is positive, one is negative? Because the moment is going out from the bottom and into the top. So the bottom part is in tension and the top part is in compression. Now, you might ask me, what is the arrow associated with this one So what is the stress here at this point? Well, let's say the stress here at this point, A. Well, the stress at this point is this. This is the stress at that point. So let me do this. This one is sigma A. This is the stress associated at that point. So you can calculate very easily because you can just take this distance. This one is the y coordinate of A. And so you can find that sigma A is mz divided by iz times ya. And since that distance is 10 millimeters, remember this t is 20, so this distance ya is 10 millimeters. This number is just 8 divided by 17.81 times 10. So let me use the calculator again. 8 divided by 17.81 times 10, 4.49 megapascals. See, and now you can find whatever point you want. Say, what is, say, the stress at this point here, point P, which is at YP, say 35 millimeters. Let's not say 35, let's say 55. Well, it's exactly the same. You draw a straight line from P. And this one is exactly the arrow associated with the stress. Oops. This is the stress, sigma P, that you can calculate because you know this. All right, any questions? I think we're done. If you don't have any more questions, let me stop recording.